Traditional RAG is evolving. We are now solving highly complex business problems by moving to agentic RAG, taking a single AI model and fracturing it into a dynamic network of specialized interacting agents. But every new agent added to a workflow introduces a new engineering challenge. That agent requires another LLM call, another prompt to process, another retrieval step, and more context to digest. Very quickly, a workflow that looked perfectly logical on a whiteboard becomes slow and expensive when deployed in a live environment. When latency spikes, the instinct is to blame the underlying foundational model. In enterprise systems, the LLM itself is rarely the actual bottleneck. This network diagram illustrates the real problem: orchestration bloat. We have agents retrieving the exact same information, passing massive chunks of context to one another, and waiting sequentially to finish tasks. The entire system chokes, and the orchestrator glows red with latency and token costs. Making an enterprise solution production-ready requires architects to treat efficiency as a core engineering requirement, equal in importance to agent capability. Performance engineering cannot be a patch applied after a system is built. It has to be a core architectural pillar from day one. This blueprint details a methodology called the SMART framework. It's a systematic approach to eliminate orchestration bloat, reduce token consumption, and cut latency. The 5 pillars are: select less, model smart, avoid redundancy, reduce context, and think in parallel. Together, they tackle the problem at every level, from routing and memory to context size and execution speed. We are going to take a bloated, linear multi-agent workflow and systematically refactor it from the ground up using each of these 5 pillars. Adopting this structural discipline provides the control over latency and cost necessary to support high-volume enterprise workloads. We start with S, select less. A common orchestration mistake in multi-agent systems is the assumption that every request must participate in the entire ecosystem of available agents. If you have 10 specialized agents, activating all 10 every time creates massive operational drag. Each unnecessary agent adds latency, prompt processing time, and token costs that multiply rapidly at scale. Instead of asking which agent to call first, the orchestrator should ask which agents are actually needed. We do this by setting up an intent classifier as a lightweight gateway step to determine the user's specific goal before anything else happens. For example, if a user wants to summarize a policy document, the classifier lights up an active path to a retrieval agent and a reasoning agent. Tools like the SQL agent, calculator, or web search dim out and disconnect. They are unnecessary overhead. We also implement an early exit. If the reasoning agent achieves a high-confidence answer early in the chain, the orchestrator halts the workflow immediately, completely bypassing any downstream validation or critique notes. The M stands for Model Smart. Enterprise systems often default every agent's core engine to the largest, most capable frontier model available. This creates inefficiency, paying for massive parameter counts and high latency on simple deterministic tasks like extracting metadata or routing documents. The solution is a technique called model cascading. In this architecture, we examine the incoming task queue, evaluate the complexity, and assign the work to models proportionally across 3 tiers: a small rapid node, a medium node, and a massive complex node. Lightweight tasks like intent classification, entity recognition, and document routing are pushed directly to the smaller, much faster models. They execute these tasks efficiently without any bottleneck. The large frontier models are strictly reserved for tasks that actually require multi-document analysis, resolving conflicting information, or deep business policy interpretation. By matching model scale directly to task complexity, architects protect their inference budget, while maintaining the exact same reasoning quality in the final output. The A is avoid redundancy. Repeated operations, specifically when independent agents execute identical vector searches, account for more hidden overhead in multi-agent systems than poor reasoning. Think of an optimized multi-agent system like a human team. If one agent solves a problem or retrieves a file, the rest of the team should build on that result rather than starting from scratch. To enforce this, we use write-time memory. Instead of passing the entire growing conversation history to every single agent, an agent completes a task and writes its output directly into a central structured memory database. Now, downstream agents interact only with this structured memory state. They instantly access completed tasks, evidence, and pending actions without processing thousands of irrelevant tokens from the original exchange. We also apply rigorous caching. Semantic caching reuses answers to similar queries, and embedding caching ensures we never regenerate vectors for documents the system has already processed. In an insurance claim workflow, once a retrieval agent fetches the policy, the validation and recommendation agents pull that context straight from shared memory rather than performing new searches. Establishing shared memory and strict caching policies ensures the enterprise never pays the computational or financial price for the exact same operation twice. Next is R, reduce context. Dumping full documents and verbose reasoning traces into every prompt degrades model focus and increases costs. We enforce the rule of context discipline. Every agent must receive only the highly specific sliver of information required for its isolated task, and absolutely nothing more. To achieve this, we use context compression for inter-agent communication. We replace pages of unstructured text handoffs with concise, structured data payloads. The anatomy of this structured handoff is precise. It replaces paragraphs of text with just 4 fields: key findings, supporting evidence, confidence scores, and strict references. We pair this with strict output token limits and optimized prompts, preventing agents from generating narrative filler when only a binary classification is needed. Ruthless context compression consistently proves to be the single most effective optimization for delivering massive, immediate reductions in system-wide token costs. Finally, T, think in parallel. The ultimate latency killer in workflow design is building multi-agent systems like sequential assembly lines, where agents sit idle waiting for preceding steps to finish. In many enterprise workflows, these dependencies are entirely artificial. Agents are executing sequentially because of poor design. We can reconfigure these into parallel operations. By deploying parallel agent execution and asynchronous tool calls, we take a linear chain of operations, restack it vertically, and process independent streams simultaneously. In a complex workflow, retrieving policy documents, extracting invoice data, and pinging regulatory databases can all happen at the exact same millisecond. As they finish, they deposit their results into a final aggregation node. We also push heavy batch processing workloads, like embedding generation and indexing, entirely offline. This separation keeps the user-facing real-time workflow fast.